So in chapter 5, we're going to be studying thermochemistry, and we begin with an overview of energy basics, and we talk about the types of energy changes that we see when physical and chemical processes occur to a sample of matter. So the first thing that's important to recognize is that a physical or chemical change of a sample of matter will be accompanied by a transfer of energy. So for example, if an ice cube melts, then that ice cube is taking in some heat, and that's causing it to undergo that phase change. If a fuel burns, it's going to be releasing a whole bunch of heat and light. And if a substance like the gunpowder that's in a firework explodes, then the particles that make up that sample of matter are undergoing rapid motion after the chemical change. And this is important for us because we're going to be wanting to know whether the substance that we're going to react is going to undergo an explosion. We're going to want to know whether the things that we're wanting to react need an input of energy. And sometimes, we like to harness this energy to do other things with it. So we'll do a chemical reaction with the intention of not gathering the products of that reaction, but rather gathering the energy that's released. And a good example of this is the combustion of gasoline. So what do we mean by energy? Well, energy can be defined as the capacity to do work. And in physics and chemistry, work has a very specific meaning. Work means to move an object against a force. And so a good example of work would be lifting an object against the force of gravity. So if I have the capacity to lift an object, then I'm a source of energy, right? So that's a good example. One type of energy is kinetic energy, and kinetic energy is the energy associated with the movement of objects, and it's dependent upon two things. It's dependent upon the mass of the object and also its velocity. And we saw this earlier when we were talking about gases. Kinetic energy has this little formula here. The kinetic energy of an object is equal to 1/2 times its mass times its velocity squared. And the important thing to keep in mind here is that we do need to use base SI units in order for this formula to work how we're expecting. So our mass is in kilograms, which is the base unit for mass in the SI system, and our velocity is meters per second. So what can we see? Well, we can see that the kinetic energy of an object increases as its mass increases, and it increases as its velocity increases. So if we have two objects that have the same velocity but different masses, what this little formula is telling us is that the object with the greater mass will have more kinetic energy. Right? So you can think about this, if somebody rides a bike into your house at 5 miles per hour, it's not going to do a lot of damage. But if somebody drives a bus into your house at 5 miles per hour, it's going to do a lot more damage because the bus has a lot more kinetic energy. Similarly, we can consider two objects that have the same mass, but they have different velocities. So we could consider like two cannonballs, and it doesn't take a lot to recognize that the object that has the greatest velocity will have the greatest kinetic energy. If somebody tosses a cannonball at you, it's probably not going to do a lot of damage, but if somebody fires a cannonball at you out of a cannon, it's going to do a lot more damage because it's moving a lot more quicker, right? So, we kind of get a qualitative feel for how kinetic energy is related to mass and velocity. There's a particular type of kinetic energy that's of importance to chemists, and that's the kinetic energy that's associated with the random movement of particles. And this is referred to as thermal energy or heat, and it's normally given the symbol lowercase q. And so some properties of heat are that as the temperature of a sample increases, its thermal energy will increase, or or vice versa. As the thermal energy of a sample increases, its temperature increases. And what that really means is that the particles will be undergoing more random movement as your sample heats up, as your sample gets hotter. The other thing to recognize is that the average velocity of the particles in our sample of matter will increase as the average thermal energy of our sample increases, right? So the hotter our sample is, the faster our particles are moving around. So thermal energy is a specific type of kinetic energy. It's the kinetic energy associated with the random movement of particles in our sample of matter. There's another kind of energy that you'll hear people talk about. This is called potential energy. And there are a variety of different forms of potential energy, but they all have one thing in common. Potential energy of any type is dependent upon the position of the particle. And probably the simplest example to recognize is what we call gravitational potential energy, which is dependent upon the height of our particle above the ground, right? And the higher it is, the more gravitational potential energy it has. Now, it's important to recognize that gravitational or any form of potential energy can be converted into kinetic energy. So if we raise an object up and then we let it go, it will fall towards the ground. Its potential energy will decrease as it gets closer to the ground, but that potential energy will be converted into kinetic energy and it will start speeding up. Another example of potential energy that's of particular importance to chemists is electrostatic potential energy. And electrostatic potential energy is the energy that arises as a result of the position of charged particles. And this is described by Coulomb's law that says that like charges repel one another and opposite charges attract. But Coulomb's law goes a little bit further, and it says that the closer the particles are to one another, the more they interact. So the electrostatic potential energy is actually dependent upon a couple of things. First of all, it's dependent upon the size of the charges. So these are Q1 and Q2, and here indicate the charge on particle 1 and the charge on particle 2. And then it's also dependent on the distance between the particles. So this is the distance, and this is the charges. So what we see is that the electrostatic potential energy goes up as the charges get bigger, and it goes down as the distance between them gets bigger. So the further apart they are, the more weakly they interact. The closer together they are, the more strongly they interact. And so, yeah, that's how electrostatic potential energy works. And we know that electrostatic potential energy is important for us because it is the energy that exists between protons and electrons, right? And protons and electrons are oppositely charged, so they attract one another. Now, one of the curious properties of energy is that energy will flow as heat transfer, but only in one particular direction. It always flows from the hotter object to the cooler object, and there has to be a difference in temperature for energy to flow via heat transfer. So if I put ice cubes into a warm glass of water, what's going to happen is that heat will flow from the warm water into the ice cubes. And what happens? The water cools down, the ice cubes become hotter. So when heat is transferred, heat will continue to be transferred until both the objects are at the same temperature. Okay. Now, in the case of where we've got two different phases of matter, sometimes you're going to transfer enough heat that you'll actually change the state of one of the sample of matters, one of the parts of the sample that's present. So in the case of our ice cubes in water, what can happen is that we'll transfer enough heat from the liquid water into the ice cubes that will melt the ice cubes, and then eventually everything will be at the same temperature and no more heat will be transferred. So, what are our units for energy? Well, there are some non-SI units, and perhaps the most common one is the calorie, normally indicated with a lowercase c. And the calorie is the energy required to heat 1 gram of water by 1 degree Celsius. So it's almost an SI unit, but not quite, right? And the most common unit for measuring energy in the SI system is the joule, and 1 calorie is equal to 4.184 joules. You'll be wanting that for your homework problems. You'll be wanting to know this equality here in order to solve some problems. Now, the problem with the calorie is there's two versions of it. There's this regular calorie that most scientists and engineers are interested in, and then there's the nutritional or dietary calorie, generally indicated with an uppercase C. So that's how you can kind of distinguish the two, but you can see it's not a great system, right? If that's just the difference between the two. It's actually 1,000 regular calories. So 1 big C calorie is equal to 1,000 little c calories. And I guess it's just because, no one really wants to be eating 2 million calories a day, so they just made it 1,000 times smaller. So it's a little bit confusing. So we've got sort of our basic units defined, and we've got some basic terms about different types of energy: kinetic energy, potential energy, thermal energy defined. Some other things that are important to define are what we mean by the system and the surroundings. So when chemists are talking about energy and energy transfer, the system that they're talking about are all of the atoms, molecules, ions, electrons, and things that are undergoing the change. The part of the universe that we're interested in, these are the materials that are represented by our chemical equation. And then everything else that's not part of that is what we call the surroundings. So chemists have a very simple view of the universe. It's composed of only two components: the system, the things that are undergoing the chemical or physical change that we're interested in, normally represented by a chemical equation, and then the surroundings, which is everything else. You put those two things together and you end up with the universe. So from a chemist's perspective, the universe is just an Erlenmeyer flask where your reaction is occurring plus everything else. Now, something to recognize is that the surroundings does include solvent. Right? So if we have a reaction between sodium hydroxide and hydrochloric acid, it's only the actual things that are reacting that are part of the system. The solvent is most definitely, and the container and everything else in the universe is part of the surroundings. So you need to be aware of that. So when a chemical or a physical process occurs, energy will be transferred between the system, what we're interested in, and the surroundings, the rest of the universe. And the energy can be transferred in two ways. It can be transferred as heat, and that is transferred in that manner because there's a temperature difference between the surroundings and the system, or it can be transferred as work, which we indicate with a little lowercase w, when an object is moved by a force. So thinking about that explosion, right? The system is expanding, pushing back the surroundings. We're going to be moving the surroundings with considerable force sometimes. So let's just kind of have a look at this. This diagram here is indicating what is happening when energy is being transferred from the surroundings into the system as heat. And what's happening is the system is losing some energy, the surroundings are gaining some energy. Because it's being transferred as heat, it's stimulating random movement of the particles that make up the surroundings, right? They're not moving in any particular direction, the particles there, they're just kind of moving around randomly. Now, if the system transfers energy to the surroundings via work, then we're going to push those particles in a net direction against some force. So there'll be an orderly movement of the particles. So an example that is often given is when a gas expands, pushing a piston back. So the gas expands and that piston rises up and it moves in a orderly manner. All right, there we go. The gas expands and it pushes the piston back in an orderly manner. So that would be an example of energy being transferred as work. So thermochemical processes involving a transfer of thermal energy, can be described as being either exothermic if the system gives out thermal energy. And it's important to recognize that what that means is that the system will lose energy. So the change in energy of the system will be a negative number. This is what we use to indicate Q, indicates the thermal energy of the system, or thermal energy that is transferred. And so if our system is losing thermal energy, then Q will be negative. Thermochemical processes can also be classified as being endothermic, and that's where the system takes in thermal energy. So there's an increase in the thermal energy, so Q will be greater than 0. So two things to notice here is exo, it means exiting, on the outside, leaving, right? Endo means on the inside, entrance, taking in. So kind of keep that in mind, right? Exiting and entering the system, exothermic and endothermic. So exothermic processes represent a loss of energy by the system. Endothermic processes represent a gain in energy by the system. Notice how the energy change is always defined from the system's perspective. When the system is losing energy, the energy change is less than 0. When the system is gaining energy, the energy change is greater than 0. So a good way of kind of like illustrating this and getting your head straight about these types of changes is looking at changes of state, because it's very obvious to us whether these things are exothermic or endothermic. So we'll look at some of the three common changes of state. So changes from solid to liquid to gas and vice versa. So if I move from a solid to a liquid, we call that process melting, and it's probably pretty obvious to you that I have to put heat in to make that happen. That is, melting is an endothermic process. Endothermic, yeah? Now if I take a liquid and I boil it and evaporate it, I turn it all into a gas, it's fairly obvious to me that that will require an input of energy. Again, that process will be endothermic. If I go back the other way, if I take a gas and I want to turn it into a liquid, I'm what we call condensation. I'm going to have to take heat out of the system. That is, it is a exothermic change. Again, if I have a liquid and I want to turn it into a solid, we call that process freezing, and I have to take heat out, right? If I want to make ice cubes, I don't put a pot of water on the stove. I put water in an ice cube tray and I put it in the freezer, because I've got to suck the heat out of the liquid water. Okay, so this kind of like just helps us get oriented with what's going on. There are two less common changes of state that we should know the names of. That is when we go directly from a solid to a gas without going through the liquid phase. That's called sublimation, and it is an endothermic process. I have to put heat in to make that happen. Going the reverse direction is when we go directly from a gas to a solid. That's called deposition. I have to take heat out of my system to make that happen. So it is an exothermic process. So what you've probably recognized at this point is that if a change is endothermic in one direction, when we run in the reverse direction, it's exothermic. And that is true for any physical or chemical process. Okay, so when we go from solid to liquid to gas, all of the changes are endothermic, but when we go from gas to liquid to solid, all of the changes are exothermic. So this is very important to recognize. A process that is exothermic in one direction is endothermic in the other. Okay, so you don't need to know the change in energy for both directions. You just need to know that it's going to be equal and opposite when you reverse the direction. So this is summarized, or what I'm summarizing here is also important. So when a system undergoes a change in energy, there is an equal and opposite change in energy in the surroundings. So what do I mean by this? What I mean is that whatever energy is lost by the system will be gained by the surroundings. And whatever energy is gained by the system will be lost by the surroundings. Now, we tend to use the delta symbol to indicate the change in a quantity. So when I write delta U, U indicates the total energy of the system. What this means is it's the final energy value of the system minus the initial total energy of the system. Okay, so keep that in mind. That's going to be true for any quantity. If I say delta T, I mean T final minus T initial. Okay, so that's what we mean by the delta of a quantity. We mean its change from the final or from the initial state to the final state, and it's always the final minus the initial value. Okay, so whatever change in energy the system undergoes, there will be an equal but opposite change in the energy of the surroundings. So we can kind of reorganize this. The universe is just composed of two components, right? It's composed of the system and the surroundings. So if I add together the change in energy of the system and the change in energy of the surroundings, then I would get the change in energy of the universe. And because these two terms are equal and opposite, and I can just see up here that if I was to reorganize this to add these two together, see that that's always going to be equal to 0. So what that really is telling me is that the energy of the universe is not changing. I'm just moving energy around from one place to another, and whatever is lost in one area will be gained in another. So the total energy of the universe isn't varying at all, just kind of moving energy around from one place to the other. Now, I want to give you a little warning. If you start looking stuff up online, you'll often see people use an uppercase E to indicate the total energy of a system, what's often referred to as the total internal energy of the system. And sometimes people will use U. You just kind of have to look for context to understand what is meant. Okay, so just keep in mind that not everybody uses U for total internal energy. So this observation that the total energy of the universe is fixed and that we're just kind of moving it from one place to another is summarized in what's known as the first law of thermodynamics. It's also known as the law of conservation of energy. And this is kind of one way of explaining it. It says energy can be transformed from one form to another. So we saw potential energy being converted into kinetic energy earlier, and it can be moved from a system to the surroundings or vice versa. But what it can't be is either created or destroyed. There's a fixed amount of energy in the universe. We can change its form. We can move it from one place to another, but we can't get any more, and we can't make it disappear. Okay, so basically what this really means is you can't get something for nothing. All you can do is take it from one place and move it somewhere else. Okay, so we saw that when energy is transferred as work, that means when we make an object move against a force, there are two possible scenarios. We could have work being done to our system that is increasing the energy of our system. So a good example of this would be if our system was a gas and we compressed it. Or we could have our system actually like doing work, right? So the system is pushing on the surroundings in some way, and the system is losing energy and the surroundings are gaining energy. And a good example of that would be when a chemical reaction could like push back a piston, like the piston in the engine of your car. Okay, so that's something to keep in mind. So we will talk about work being done by the system. The system is losing energy, and we'll talk about work being done on the system. The system is gaining energy. Now, energy can be also transferred to or from our system in the form of heat. And we were going to talk about heat being absorbed. That's when our system is gaining energy as heat, or heat being emitted. That's when our system is losing energy as heat. And it turns out that the heat absorbed or emitted by an object is directly proportional to its change in temperature. So the bigger the change in temperature, the more heat that is being lost or gained. All right. So this is kind of mathematically, we indicate that here, that the heat transferred is directly proportional to the change in temperature of the object. Or a little bit more math, we can say that the heat transferred is equal to a constant multiplied by the change in temperature of our object. So what is this constant? This constant is given the name the heat capacity. And what does the heat capacity represent? It represents the energy required to raise the temperature of the object by 1 degree. So in SI units, that's going to be by 1 degree Celsius. So the heat capacity, which we indicate normally with the symbol uppercase C, sometimes with a little subscript P there, but always the uppercase C of the object, is the energy required to raise the temperature of that whole object by 1 degree Celsius. So another way of writing this, and your book uses this, this form of it, is that the heat capacity is the heat transferred divided by the change in temperature of your object, and that there is in degrees Celsius. And we know that delta T is T final minus T initial. Okay. All right. So these are like, this is for a whole object, right? So like, you know, if we have a pan that I'm going to heat up, then it would be for the whole pan. Okay. So it's for every single object that we were studying, we'd have to define a unique heat capacity. That could get a little weird, right? You know, if I have like one iron pan that has a certain mass, it would have a specific heat capacity. If I had another iron pan that had a different mass, it would have its own heat capacity. Every single object that we wanted to study would require its own heat capacity. Because that's kind of awkward, we've defined what is known as the specific heat capacity, and we give that the symbol lowercase c. And this is a very useful quantity. It's the quantity of heat required to change the temperature of 1 gram of a substance by 1 degree Celsius. So now we don't have a heat capacity for every object. We have a specific heat capacity for 1 gram of a particular substance. And so it becomes a lot more applicable. So using this form of the heat capacity, we can now write that the heat transferred is equal to the specific heat capacity multiplied by the mass of the object multiplied by its change in temperature. It is important to realize that the specific heat capacity, and in fact just the plain old heat capacity, does depend on the state of the substance. And you can see here when we look at water that liquid water, solid water, and gaseous water, here they are, have quite different heat capacities. In fact, water vapor has a heat capacity that is less than 1/2 of liquid water. So it changes a lot, right? And even going from water to ice, they have very different heat capacity. So if you get those confused, you're going to be in trouble. So make certain that you do pay attention to those physical state symbols. Okay, so let's do a quick calculation using a specific heat capacity. So it says a layer of copper welded to the bottom of a skillet weighs 125 grams. So you got, decent slab of copper on the bottom. That's the mass of our copper. And then it says how much heat is needed to raise the temperature of the copper layer. So that's going to be our Q. That's what we're trying to solve for. From 25 degrees Celsius, that's going to be our initial temperature, to 300 degrees Celsius, that's going to be our final temperature. Okay, so the mass of our copper is 125 grams. The specific heat capacity of copper is given. Here it is, 0.387 joules per gram per degree Celsius. That's our CS there. And then our delta T we're going to have to calculate. Remember, it's our final value minus our initial value. Okay, so the temperature of the copper, we want it to go up 275 degrees Celsius. So now we just use our little formula here, Q equals MCAT. So M, 125 grams, our specific heat, 0.387 joules per gram per degree Celsius, and our delta T, 275 degrees Celsius. So grams cancels, degrees Celsius cancels, degrees Celsius, leaves us with joules. And there is our answer. 3 significant figures. It's going to work great for this. Okay, this guy had 3 sig figs. This guy had 3 sig figs. This one had 4 sig figs. So when we multiply everything together, we want to get 3 sig figs. Okay, so let's try another one. This one's going to be a little bit more complicated because we're going to have to do an additional conversion. It says find the heat transferred when 5.5 liters of ethylene glycol, and then it gives the density and the specific heat in a car radiator cools from 37 degrees Celsius to 25 degrees Celsius. So that's my initial and that's my final. So what do I know? I know that Q equals MCAT, right? So I need my mass. I'm not given my mass, but what I am given is my volume and my density. So to get my mass, I'm going to do my density times my volume. So I got 1.11 grams per milliliter, and then I've got 5,500 milliliters because I've got 5.5 liters. So I've got like 6,105 grams. Okay, so that's my mass there. So 6,105 grams, and then my specific heat is given 2.42 joules per gram per degree Celsius, and then I've got to do my delta T. My T final was 25, and my T initial was 37, so it went down by 12 degrees. So it's important to get these around the right way, these temperatures here, because that's going to give us the correct sign there. So what was Q? Q was equal to minus 1. Oh, no, I should point that out, that's degrees Celsius. That cancels. Good practice here, right? Grams, yep, leaves me with joules. So here we go. It ends up being minus 1.77 by 10 to the 5 joules. So the minus sign tells me that heat was lost. Okay? All right, heat was lost from this system as it cooled down from 37 degrees down to 25 degrees. It makes sense that heat should be lost. Okay, so remember what we said? We said that heat will spontaneously be transferred from a hot object to a cool object. So if I have a cold object and I bring it in contact to a hot object, what will happen is heat will move from the hot object into the cold object. The temperature of the hot object will go down, the temperature of the cold object will go up. And when will the heat stop being transferred? When they reach the same temperature, okay? Once they get to the same temperature, that's called thermal equilibrium. Now, in this case, it ended up being the average of these two numbers. It is almost never the average of your two initial temperatures, the temperature at thermal equilibrium. So please don't think that that is a consistent idea. According to the law of conservation of energy, the heat that is lost by the hot object must be equal to the heat gained by the cool object. So sometimes we will write Q lost equals minus Q gained, or we'll write alternatively Q lost plus Q gained equals 0, and I hope you can see that they are equivalent statements. I like to use this form because it saves a lot of rearrangement. Okay, So here is the big question that, the long-winded question that is appropriate for section 5.1. It's what we call the thermal equilibrium problem. Sometimes people will talk about the skillet problem. If you hear people talking about that, because that's often given as an example, is a skillet that is comes into thermal equilibrium with another object. Okay, so it says a 5-gram piece of iron at 100 degrees Celsius is dropped into 100 grams of water at 25 degrees Celsius. So what I know is that the cold object is the water, and the hot object is the iron. Okay, so what's going to happen is that the temperature of the cold object is going to go up, and the temperature of the hot object is going to go down, and then they're going to reach the same temperature and heat will stop moving and they'll be at equilibrium. So for us, this is what this problem is all about. It says, what is the temperature of the water and iron at thermal equilibrium? So the hot object is going to lose energy. So Q lost will be equal to mc delta T. So this will be equal to, and we were told that we had 5 grams of iron. We're told that CS is 0.45 joules per gram per degree Celsius. And then delta T, T final we don't know, that's what we're trying to solve for. And then T initial was 100. Okay, so that's that. And then for the water, Q gained, we've got 100 grams. Again, it's going to be MC, let's write that a little neater. MC delta T. And so this is going to be equal, we had 100 grams of water. And then C was 4.18 joules per gram per degree Celsius. And then my delta T is T final that we don't know, minus the initial temperature of the water, T initial, which was 25, and that's degrees Celsius. So there we are. So what I know is, according to the first law of thermodynamics, Q gained is equal to the negative of Q lost. Okay, so Q gained was 100 times 4.18 times T final minus 25. And then that is equal to the negative of Q lost, which is negative 5 times 0.450 times T final minus 100. So what I've got to do is rearrange and solve for T final. And what I find the easiest way to do this is to put it into an online solver, such as like that found in Wolfram Alpha. So I'm just going to kind of like write this down now. 100 times 4.18 times T final minus 25 is equal to, and it's important, don't drop the minus 5 times 0.45 times T final minus 100. So I'll just pop open a web browser. I'm going to go to Wolfram Alpha. Wait for it to kick in. Of course, as I'm demoing it, it's being super slow. There we go. And I'll put this in. 100 times 4.18 times, and instead of putting T final, I'm just going to put X minus 25 equals minus 5 times 0.45 times, and instead of T final, I'm just going to put X minus 100. And then close that. Now what do I know? I know that my X, my final temperature, is going to be a little less than 100 and a bit more than 25. So let's see what we got. Solve it. There it says X equals 25.4. So 25.4 degrees Celsius. So we said that the temperature of the water should go up. It has. It went up by 0.4 degrees Celsius. And we said that the temperature of the iron should go down, and it has. It's gone down all the way from 100 to 25.4. And what you can see is the temperature of the water didn't move a lot, but the temperature of the iron moved a great deal. And the reason is because the water has a really high heat capacity. It takes a lot of energy to move the temperature of water a little bit, whereas it only takes a little bit of energy to move the temperature of the iron quite a lot. And so the temperature changes are not going to be equal, right? They're not going to be equal and opposite temperature changes. The one with the greater heat capacity is going to be more resistant to changing its temperature. Okay, so what would one do if you didn't want to use an online solver? You would have to do algebra, and you'd have to distribute all of this, then rearrange and solve for T final. Now, we're quite fortunate in that we have the capacity to use a solver in this case. Okay, so that takes us through in quite a bit of detail some of the basics regarding energy, and we've worked through some of the more complicated problems, so hopefully that gives you a really good foundation for finishing off this section.